Hello and welcome to VitoshAcademy. Today we'll be talking about linear regression again. As you see, I have probably a lot of linear regression videos and articles, probably since 2013 here. But still, there is always something interesting about it, or at least I like to think about it this way. Today we'll be talking about this formula, which is not present here, but here. It's called x times x minus 1 divided by 2. It is the so-called sum of arithmetic sequence. So, for example, if x is in our case 4, the sum of the first 4 numbers is simply 6. If x is 5, in our case, in every case actually, not just in our, the sum of the first 5 numbers is 10. Yes, as simple as that. You may know it as a formula for triangular numbers, but today we'll be discussing it. So let's start with importing all the data in our Jupyter lab. We will be using NumPy, Matplotlib, sklinear, and that's it. I'll split the precision separately. And let's start filling up the code. So pretty much that formula can be described this way. It will be called the true function. And it would be MP array. G type would be float. And it would be returning, as I mentioned, x times x minus 1 and everything divided by 2. So let's just try it. True function, what did I say here? For 5, it should return 10. Yes. Okay, yeah, I'm just thinking about stuff. Yes, it returned 10. That's great, so to say. Let's give the arrays. Our arrays would be MP array, and I'll be using pretty much 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then 12, 15, 20, 30. Let's put 40 as well. Dot reshape minus 1, 1. What did this give us? This gave us MP array in a nice shape. Yeah, see the shape here. Okay, what else? We'll get the y's and we'll be using the formula trueFN x.ravel. Let's see the y. Yeah, works. What xravel does, pretty much it gives it into nice function, not function, into nice formatted array, or at least I think so. The correct mathematical term is that it returns a contiguous flattened tensor, but okay, we'll live without it, without us memorizing it. Okay, so the x is MP sort x on the axis 0, fair enough, and y true on axis equals true function axis ravel. Yeah, does it work? Y true. Yeah, it works. Great. So why do we need the axis and the x differently? Well, here the axis, the idea was that they are sorted, not that here they are not, but imagine that you have not sorted them. It's good to have them sorted. And also, yeah, we can plot it now nicely. So let's plot and see what we have. I mean, we're gonna get this one, but just part of it. It's not gonna be that easy because we don't have all the points. We have only part of them, but let's see what we can achieve. So POT scatter, and let's scatter the axis in the y and label them data. And then see PAT show. What do we have? Well, we already have the plot. That's great. Do we need something else? We need a legend. And what? The labels. There is a special place in here for those who do not label their axis. X label would be named X. Y label would be named Y. And what else? Title. Y equal X times X minus 1. This one for every case in parentheses, divided by 2, and this one here as well. So let's see what we got. Oh yeah, looks okay. We can make a tight layout. I saw this somewhere and I liked it. Not sure how much does it bring to us. And additionally the fixed size. Yes, POT fixed size. POT figure fixed size. And it's gonna be 7 by 4.5. Now it's better. Okay. So once more, what do we see here? We see it differently than the one here, definitely. Most probably because the X is different. We only have 40 here, and we have here like in the thousands. Like 1,000 would be here, so it's easy. So it's obvious that 1 centimeter on this one is quite different than 1 centimeter on that one. So the curve is looking like not exactly the way it should be looking. The way it should be looking is on this one. Okay, so let's continue with our regression. So what do we do? What's the idea of the whole regression? The idea of the whole regression is to make a line for the linear regression, saying that this way, the way we made the line, is the optimal line that makes the errors, the squared errors between the dots minimal. Or with other words, let's see. So linear regression dot fit, and it's gonna fit between the X and the Y. Now, yeah, linear regression is a function, and then we're gonna code this function and we're gonna code the fit like this. So let's see, what do we have here? Wow, we actually have something interesting. It's something new, I didn't know it. We have jobs, positive, we have it fitted, and we have even the documentation for the linear regression SkyKit. Okay, this is where Jupyter Lab goes probably better than the other one, Jupyter Notebook. Okay, so let's see what the M is. In the general case, M is the slope. It means rise over run. Okay, so for how many of this, for one line of X, how many Y's have we increased? But in this case, we can just get it from here, lint coefficients underscore, and we are going to say we want the first coefficient, and it is this one. It is 18. So for 18 lines of X, for one line of X, we get 18 lines of Y. Does it make sense? Let's see. Yeah, we can say so. Okay, not the whole time, but somewhere here in the regression line, it happens like that. Yeah. So we see the M, let's see the B. And it's gonna be just len dot intercept. And it finishes with an intercept. So it's gonna be on -100, so somewhere here is the start of our linear regression line. It's gonna look like this. Imagine I'm going to write it like right now. Okay, it's gonna be something like this, or at least this is what I hope. Let's see how it's gonna look. We can print the M and the B. Linear fit formula equals y m dot 2f. This means up to the second decimal times x plus b 2f. Yeah, pretty much. Something like this. Yeah. Just with this, it is enough to make a line. So we would start it at -100, and for every y, for every 1 x, we are going to get 18 y's, which is the slope. Okay. So far so good. Let's show this one. I'm just going to copy this one here, and I'm going to improve it. How do we copy it? How do we improve it? Scatter, label data, glazed. Now we have to plot. So we plot the axis, y true on axis, label true curve. Let's see what we got. Well, we pretty much get this one, but with the dots. That's great. And now let's get the y line on axis. How it is going to look like, no one knows because we haven't made it. So I'm just going to comment it here. And somewhere here I'm going to say y line on axis. That should be enough. And it's gonna be equal to len, our linear regression model, and then predict. And it's gonna predict on the axis. Great. Let's see how this one looks. I'm just curious. So did something happen? Yeah. Y line on axis. Let's see how this one happens. Yeah. We simply get some points. That's great. And if you are interested what these points are, these are the points in order to make a straight line for each x that we have given, so to say. So for 1, it would be this, for 2, it would be that, for 3, for 4, and then we get into the positive ones, because we are working with lines. Okay, so let's plot it. How do we plot it? The same, we have the axis, and we write one line on axis, and the label would be linear fit. Yeah, this is how it looks like. You see the 0 is here on the y, so we are in the minus at the beginning, minus 81 something, and so on. So it is obvious that our linear fit is actually failing, but this is what you should be expecting when you try to fit a parabola part with a line, especially into such a range around x. And that's why we have to make something like quadratic regression with polynomial features, and we're gonna try to make to print the formula. So poly2 is pipeline, and then we're gonna fit x and y. And let's see what do we get into this pipeline. First, poly equals polynomial features, degree equals to include bias. We don't have bias. And now the AR, which will be the linear regression. And it's a function. This is what we discussed. Great. Let's see what poly2 gives us. Well, it gave us a pipeline with linear regression and polynomial features. Second degree means that we have x squared somewhere. At least this is what I remember from university. Yeah, so that's like the minimum. Minimum to have something interesting is 2. Yeah. It's actually interesting, poly. Okay, so the coefficient. The coefficient should be easy. Poly2 dot named steps LR dot coefficient. Great, we got a coefficient. So minus 0.505. What is this? This is the coefficients here after we solve this one. After we solve this one, actually, it's like x divided x squared for the first part minus x. And x squared divided by 2 gets us a coefficient of 0.5 in front of the x. This is how it works. Okay. The rest I'm going just to copy and paste it, not explain so much. And this is our formula actually. So 0.5 times x squared plus minus 0.5 times x. And this one for c we got nothing, so it's minus 0. And this is actually the same as this one here, simply recalculated. The interesting thing is that our beloved magic with the polynomial pipeline actually got it the correct formula without knowing it. It only knew the input and the output, and like the x and the y's. X is input, y is the output. It's kind of interesting that it did it this way, and it's rather good. Yeah, I mean, you shouldn't be expecting something else. I mean, when it is a quadratic formula, maths and Python and all these fancy libraries, they are like magic. Okay, so at the end, let's make a final comparison at the real x values. And it is going probably to pretty much what I'm expecting to see here. Our 3 lines, we have the linear fit, the quadratic fit, and the true curve with line style, this one. And I'm expecting that 2 of them would fit perfectly. Yes, the true curve and the quadratic curve are like perfect. They are literally the same. So that's because the true curve and the quadratic curve have the same function. Like this one here is pretty much the same as this one here. So far, so good. Let's make a quick recap. This video is made just in once, so it would be like hopefully around 20 minutes or less. So let's take a look. We were talking today about graphic functions, and this function is actually a famous one. For example, if you want to know the first 15 numbers and their sum, if you plot this parabola, you would see that the sum of the first 15 numbers in mathematics should be somewhere here. So 1 plus 2 plus 3 plus 4 should equal around 105. And this is what we were trying to plot today. This is our data. Let's make it a bit more interesting. Let's put 12 and let's put here, I don't know, 11 and 13. See, because it sorted it out, 11 and 13, they are now here. We can put 100 so it's visible. Okay, 70 is better probably. 50, it will stay with 50. So it is on the same one. So we scattered the values. Then we used linear regression to calculate all the others. And we fitted a line with this one, with this magic here, y line on axis. Pretty much what we did is we taught the Lin model to predict based on the axis, the y line on axis. It gave us its values and we managed to fit it. Yeah, I mean, getting a function and with a linear fit line is always challenging. Usually doesn't work. Here it doesn't work obviously quite well, but it is something, and this is what linear regression actually is. And just to make more interesting, we made a polynomial regression, and because our function is actually really simple polynomial function, it matched perfectly. So if you have any questions, ask below the video. I hope you enjoyed it. Take care of yourself. Goodbye and enjoy the rest of your day. Bye.